Okay, today's lesson is about deep generative models. So we have learned about neurons, artificial neurons, single layer perceptron, multi-layer perceptrons, feed-forward networks, convolutional neural networks, linear sequential models like RNNs, GRUs, and LSTMs. And then we learned about transformer model, and we have learned some of the uh, advanced learning techniques that can be used for deep learning. Right, so today we are going to discuss about another very important and very modern trending uh, type of deep learning models, which are generative models. Right. So let's see the differences between the classification and regression models that we have learned in most of the cases, and the difference between the generative models that we are going to discuss today. Right? Uh, all the lessons that we have covered are about supervised learning algorithms, right? So classification and regression models are generally using supervised machine learning, where we have a we should have a supervised uh, uh, machine learning, so that we should have a labeled data set. But in generative models, most of the time they are involved in unsupervised machine learning, but sometimes there are, right? Sometimes there are supervised machine learning techniques as well, right? But for pre-training for some of these stuff, that means we are using unsupervised machine learning. Because we will see why what is the difference between why we can use unsupervised machine learning for generative models, which is very cheap when it comes to uh, the model training and finding data sets, because when it comes to supervised machine learning, we need labeled data, right? So that is one of the reasons why the generative models are getting much popular, because you can find a lot of data which can be used for unsupervised machine learning, right, compared to supervised machine learning. Right? And when it comes to the features or the inputs and outputs, when it comes to classification models, generally what we are doing is we have set of X features or X inputs, so X independent variables, right? So, and we are going to predict the Y values. Y value can be either a class or a value, right? Classes are used when it comes to classification problems, and Y are values when it comes to regression problems, right? But when it comes to a generative model, X features are used as usual, but the idea of using generative model is basically about generating a probability distribution function of PDF out of data, right? So that means when you have a certain set of data, we are going to find what is the probability distribution function which has generated those data. Right? So the idea of generating this probability distribution function, or the PDF, is about generating data samples. Right? So it is common for this thing for the classical for the other classification regression models as well. But when it comes to these models, especially creating a probability distribution function is important, because the main objective is to generate samples, right? So when you have a set of data, and if you can predict what is the distribution probability distribution function of each of these data points, then you can generate similar data points which may be part of the dataset or maybe out of the dataset, by taking samples out of this, by sampling from the probability distribution function, right? So in some cases, generating the PDF is important, but sometimes generating the samples is enough, right, when it comes to generating model. So we will see which of them are used for each of the requirement, right? And when it comes to classification and regression models, generally we are using these things to take decisions. Like if we want to, if we have a data set and we want to see whether it's a cat image or a dog image, so that means we are going to take decisions. So okay, this is a cat or this is a dog based on the data that we are given. Right? But when it comes to generative model, the idea is mainly about generating more information. Right? So for example, the best way that you can think about is requiring to get more data, right? Like data augmentation. So if you want more data out of a data set, so you can use generative models. Or if you want something like create some music, create a video out of the data that you already have. For example, if you have a certain musical, uh, certain type of audio clips of music, and you want to have generate a new music out of this music, so you can use generative models. If you have your own videos and you want to create your own video without you involved in recording the video, then you can use generative models. And when it comes to generative and regression models, generally classification and regression functions are used. Classification functions and the regression related functions that we have learned. But when it comes to generating a different way is used, so we will learn how those functions are. What is the difference between these functions that are used in generative models and classification models. So this is what it really means, right? So when it comes to probability density function estimation, what we have is we have got a set of data points. These are the data points, and we are going to predict the probability distribution function, right? And when it comes to sample generation requirement, it's all about we have a set of input data, and we are going to predict uh, the generated samples out of the uh, data set, right? So that is those are the main objectives of generative models. So what are the uh, idea of using the requirement of using why we are using generative models, right? So one of the requirement is that you can use this for debiasing. Say you have a data set and your data set is taken from a certain data distribution, which is a restricted data distribution. That means in practice, when you collect data, you can't practically collect a very generalized data set, right? So your data set may have certain biases, right? So what you want to have is a data set which are out of those biases. So you can use generative models so that you can identify the features and then change the weights for each of the features to generate another data set which is most of the time out of these biases, right? It is something like this. So suppose this is the data set you have got where uh, so this is an ideal situation, right? So where you have homogeneous skin color and pose, where all the data are in a certain way, but what you want is some data set like this which is very diverse, right? So their skin color, the pose, the way they are looking, the illumination, how the light is put on their faces, those are different. So whether they are wearing glasses, they are laughing or not. Excuse me. Those are different, so that you can use So this is suppose this is what you want to have, and but what you have is a homogeneous skin color and a pose. So you can use generative adversarial networks to or generative AI to create a diverse set of data for the data set that you have. And when it comes to detecting the outliers, that is another benefit that you can get from the generative models. For example, when you find that your dataset doesn't contain enough outliers to train for the edge cases, for example, when if you are training your dataset for a self-driving car, then you should train your the self-driving system to learn about the edge cases, like when the pedestrians are crossing the road, uh, when a dog is sleeping in the road, and so on, where there can be rare events that can happen, which may not have been that much frequent in your dataset. But with generative models, that you can identify the low frequency features, and then you can enhance the weights of these features, and you can train more for these outliers so that your model can learn more about the outlier situations. Right? For example, say this is the distribution function of the probability distribution function for your self-driving car, right? So in most of the in 95% of time, so the view would be like this, where it is sunny, high, it is a highway which has a straight road, is very clear in front, but in some rare cases, in low probabilities, there can be edge cases like the airplane is flying near the road, or it's going to be landed on the road. So yeah, you should take some action. And there can be some harsh weather conditions like hail or landslides or something like that, or some pedestrians are uh, crossing the road in the wrong time and so on. Yeah, you can find, but those things also can be detected with generative models, and they can be trained with your model, the supervised learning, self-driving car model, right? And in when it comes to generative AI, one thing that you have to know about is the latent variables in the model. Right? So in latent variable models are the models that have hidden or latent variables. So the meaning of latent is that it cannot be uh, seen or identified by humans. Humans means it cannot be seen outside, but there's something inside, right? So those variables are like the governing hidden and secret variables that are governing what you are seeing and what you are observing in your environment, but you can't see how these variables are acting, where they are, right? For example, when you are looking at something by your eye, so what you see are some pixels, right? So in the image, what you see are the values of pixels. So, but pixels are not the values of the pixels are not what are actually governing the content or the theme or the structure of your image, right? So there can be some other variables, hidden variables, which are governing what you are looking at, right? So for example, when you look at the face of a person, whether that person is angry, whether that person is laughing, whether he's looking upwards or he's looking downwards, uh, whether he is in a good mood, or all those things are hidden variable. But what you see are not those hidden variables, but some the facial uh, expressions uh, from the pixels, right? So what the variables that are governing those inside concepts, which are hugely impacting the theory, the inside or structure of the image, are known as latent variables. Right? The the important thing about these generative models is that you can these generative models can identify these latent variables. Right? So, for example, some latent variables may be uh, relevant to the position of the head, whether he's looking upwards, downwards, right or left. Those poses or the places where he is looking at can be changed by just changing these latent variables. Right? So these variables can be generated inside the neural network, right? So those variables are known as latent variables, and the neural networks that are using these latent variables are known as latent variable models. Right? So the advantage of generative models is that with these latent variables is that you can use this latent variable to generate an image as you wish, right? So that is a very uh, important finding when it comes to the actually can say it's a very important thing for the human civilization, right? So up to now we didn't know how to program uh, to generate images as we want, right? So like tuning whether a person is angry, whether he's looking upward, whether he's male or female or intermediate, or you can't change those things as simple variables, but With latent variable models, they can extract those latent variables, the hidden variables, and we have the opportunity to manually change those things and generate images as we wish. So that is actually a amazing thing, right? So that is what we are going to learn about these generative models. So, mainly there are two generative models that we are going to learn. One type is known as autoencoders, and the other type is known as generative adversarial network. So we are going to learn those two mainly, and we are also going to discuss about much more improved version of these autoencoders known as diffusion models as well. So this is how the autoencoders are making predictions. So as we discussed earlier, so these autoencoders are unsupervised learning algorithms. For example, you can give an image as the x value, the pixel values of an image as an x value. And these are like some of the layers of the neural network, which can either be dense layers or feed forward fully connected layers, or they can be some convolutional layers, right? So depending, so there are in convolution layers also there are different architectures, right? Some of them we have discussed, and those layers can be used as the layers. So we are not going to discuss about these layers in today's lesson, but we are going to discuss about how these generative models are designed. Right? So inside these designs, when you are going through each of the architecture separately, then you will find what are the types of layers that we are using in this architecture. So this autoencoder architecture, we just say that there are layers like this in the autoencoder, but we are not going to explain what each of the layer is like. Right? So the idea is that what we are going to explain is relevant only to the size of the image main. That is our main concern, right? So in here you can see now the image size, the size of the x vector, which is a very large one, because you should have all the values of the pixels, and in each of the layer, the upcoming layer, you can see the size is reduced up to a certain layer which has the smallest size, which is known as the bottleneck, right? So here we represent it with Z. And then again, we increase the size in each of the layers. And finally, we come up with the final layer, which has the size similar to the size of this X, right? So when we denote the input as X and the output of this autoencoder as X hat. So this is the architecture of an autoencoder. So let's see what is the idea of having this architecture, right? So mainly look at this Z layer, right? So this is the smallest layer. That means the layer with the smallest number of dimensions. So when you think about the flow of the information throughout this neural network, what you can think is that from in this layer you can get a lot of information. It can encode a lot of information, but when it is passed to the next layer, some of the information may get lost, or they should get compressed to pass to this layer, right? So when the size of the layer is reduced, because the number of parameters in each of the layer are getting reduced, the amount of information each of them can contain are getting also reduced. So you should either filter some of the non-significant information and only keep the most significant information when the size is reduced in each of the layer, right? So this is the smallest layer. So this should contain the most compressed and most efficiently kept type of information with related to this x vector. Right? So in other words, Z is like a compressed version of this x vector. Right? Because what it is trying in autoencoder, what it is trying to do is we are going to recreate this same this x vector with x hat. So in other words, what we are trying to do is we are trying to give some, for example, an image as the vector. So you can take the pixels of this image as this x vector, and we are going to when you are going to pass this image through this autoencoder and get an output, and we are going to find the difference between this input and this output, right? So the output size is also similar to the same as the input size x, right? So x hat is same as x hat has the same dimensions as same as the x. So you can compare these images, the generated image to the source image pixel by pixel. Then you can compute the loss or the loss function of this autoencoder using this mean square error, right? So you can reduce each of the pixel value from x minus x hat, and you can take the square, and either you can divide it by the number of pixels or not, right? So in this way, you can find the loss function of this autoencoder, right? So what we are trying to do is we are, for example, we can give some sample data as images, and we are finding whether this our objective is to get the same image out of this autoencoder without much difference, right? So, but there would be a difference because some of the information may get lost because because when you are propagating through this section of the autoencoder, your information will get compressed, or some non-significant information will get lost. Right? Only the most significant information would be preserved in this Z vector. And here we can expand the Z vector one by one and trying to recreate the X vector. But there may be some information lost. That's why you can see this image is kind of blurred when it is returned from the proton as the X hat output. But it is kind of similar. So what we are trying to do is our objective is to make these two images similar. So we are trying to, so we are calculating the loss function as the mean square error, and we are trying to reduce this error loss, right? So this loss is also known as the reconstruction loss. The reconstruction means we are trying to reconstruct this image as the output. So this is the loss that is relevant to this reconstruction effort, right? So one of the advantage of using this autoencoder is that you can remove some noise information from an image, because noise information are rare information. That means they are not common in all the images. They will get cancelled out when you are passing through a bottleneck like this. So these kind of autoencoders can be used to generate noise information, or sometimes you can use to fill some small missing information in an image, because these Z vector only contain the significant information about this image. Noise information like small missing values and added values will be removed when you are trying to move this information from through this autoencoder. So autoencoder is a unsupervised learning technique, because you don't have to have a label, because you are using the same X value as the output label. So this is a very good example for unsupervised machine learning for image kind of data, right? So this is not used only for image, but there are some other applications, so we will discuss later. So this is how the autoencoders work. So this is the primary form of autoencoders. generative AI. So this reconstruction quality, as I said, is dependent on the size of Z, right? Or this vector, right? So if this vector size is large, so if it is 5 dimension, so this Z vector is also known as the latent space or the latent vector. When it has higher number of dimensions, it is much more clear, right? So this is the ground truth. Ground truth means the real X value, X values, when you are using the MNIST data set, as this in this example, when the X has 5 dimensions, it is very clear when it comes to the X hat, but if the Z has only 2 dimensions, then it is a 2-dimensional latent space, then the output of this autoencoder, which is X hat, would seem like this, which is not that clear compared to this 5D latent space. But still you can see that, right? So when the dimensionality is reduced from 5 to 2, still you can read this data, right? So because even in this 2D space, the Z was able to preserve the most significant information, which is corresponding to each of these numbers, right? So that is why you can still read this latent space when you can read this X hat value or the output value even when the latent space is reduced more than half, right? When it is reduced in the size from 5 to 2, still you can read it because it can compress the information, preserving the most significant information. So when you are representing an autoencoder, we are no more going to draw them as a set of a sequence of layers because there can be arbitrary number of layers. So what we are interested is we want to show that we are reducing the number of dimensionality of the vector in each of the layer, and we are going to reduce the number of dimensions when it comes to this phase, right? After this phase, we are trying to increase the number of dimensions and come up to this final state. So from now onwards, we are going to use these types of shapes to represent the encoder and the decoder, right? So moving the information from the X to this latent space is known as this operation is known as the operator is known as the encoder, and decoding this latent vector to X hat and try to reconstruct X is known as the decoder, right? So it is trying to decode this compressed information into the original format. So when you are training this autoencoder, both encoder and the decoder will get trained. And the values of this Z vector is the most compressed form of information that is stored to represent this data set, right? Which is a compressed form of data set where you can not the form of data set, but how their structure is preserved inside this Z data set, right? So from here onwards, we will be just drawing this encoders and decoders in these kind of shapes, but not in sequence of not a sequence of layers. So up to now, what we have discussed were about autoencoders. But when it comes to autoencoders, the problem is the Z vector which was learned is highly corresponding to the data set that we have used, right? So the data that can be generated from the decoder, in this example with this one, is highly restricted to the data set that we have used, right? But there's a new innovation known as variational autoencoders, where you can consider this Z vector or the latent vector as a distribution of variables in a very constrained environment. Right? So what I say is that if you want to compress this X vector as much as possible, you can mathematically prove that this when you are trying to compress this X vector as much as possible, when you are trying to keep all the information and compress them as much as possible into this Z vector, each of the variable in this Z vector would follow a normal distribution, right? Because that is how the things naturally occur in nature, right? So you can mathematically prove that that is how it should happen. So we are not going to prove it. So each of the variables in this Z vector can be considered as taken from a normal distribution, right? So instead of having these weight vectors as they are, if we can find, assuming before that, we can assume that this Z vector is a normal distribution, right? But in practice, it may not be exactly a normal distribution, but for the purpose of our requirement, because we want to generate some arbitrary data from this decoder, right? So what we want to do is we want to generate some arbitrary information data from this autoencoder, which are coming out from the distribution of this data set, right? So what we want is we want some data generated from this distribution, which are not exactly the same information that are there in the data set, right? For example, if X is an image set, we want to create some images that are not there in this data set, right? So for that, what we do is so this is the latent vector which may contain the most critical, most significant information of this image data. So we create, instead of using the exact Z vector, we are finding the mean or the mu value and the sigma value or the standard deviation of each of these variables in this Z vector, right? So instead of having a fixed deterministic values for this Z, we are going to make this layer a stochastic layer. That means we are going to take so when you are asking some information from this layer, instead of directly calculating the calculating the values by multiplicating with some weight matrices, what we are doing is we can sample from the distribution which has a mean of mu and a standard deviation of sigma, and you can get some arbitrary values as the Z vector. So each time you ask for a Z vector, it would arbitrarily give some values for the weight vectors in the Z layer, so that these X hat images that are generated from this decoder layer will be different from these original images, but would belong to the characteristics of this, or it would belong to this distribution of this image set, data set, but be different from the data points that are given in this data set, right? So that is the innovative part, or the creativity that can be achieved with this variational autoencoders, right? So when it comes to training these variational autoencoders, because this is a stochastic layer, that means this is because this is not deterministic, so we will have to extract this to a, extract this extract some of the parameters into a normal distribution, standard normal distribution, and so on. So we are not going to discuss it here, right? So what you have to know is that you can use this kind of instead of using this z vector as the weight vector, we can have two vectors for mean values and the standard deviation values for z layer, and you can generate data randomly. That means you can sample from this normal distribution when you want to get values for this z layer. So when you are generating, when you're calculating the loss function for this variational autoencoder, because this variation autoencoder is no more a deterministic neural network, their values are determined by probabilities, right? So from here to here, you can see the probabilities are defined by q phi, where when the x is given, the z value, right? So when the x is given, the input is given, what is the z value? That is how the encoder probabilities are calculating. For the decoder part, you can assume, right? What are the theta values? So theta values are the parameter values for this decoder. So phi values are the values for this encoder, right? So p theta values is x values given the z values, right? So, and when it comes to, so those are the probabilities that are created that are relevant to encoder and the decoder. The loss function is not only the reconstruction loss, as we have seen in the autoencoder, but there would be another term, which is known as the regularization loss, added to this variational autoencoder to calculate the loss. So why we are using this regularization term is that other than making sure that this input sample input vector is same as the output vector, which is computed by the reconstruction loss, we want to make sure that this z vector follows a normal distribution, right? So when you are training, we want to make sure that z is following, values of these variables in this z vector should follow a normal distribution. So we try to find how much the values in this z vector are away from a normal distribution. So what we are trying to find is how much the values in this z vector are diverging from the normal distribution. So in order to find how much it is a certain distribution is diverging from a normal distribution, one of the mathematical technique that can be used is known as the KL divergence. So here we are using the KL divergence term to find the value that is relevant to the regularization, which is relevant to the diverge, how much the z vector is diverging from the normal distribution, which can be specified by this regularization term, right? So when it comes to the calculating the loss, you calculate not only the reconstruction loss, which is the mean square error between the given image and the created image, but the regularization loss, which is relevant to the KL divergence from the z value to the normal distribution specified by this mu and sigma, right? So those two should be added to get the total loss. So this is the formula for the KL divergence for sigma, mu, and values for each of the vector points, right? So when you take a certain variable in this z vector, which is a latent variable, right? So as I said earlier, these latent variables can govern how the image looks like, right? So if you take a certain variable which is relevant to the head pose of an image, if you change the value of this variable little by little, keeping all other variables constant, you can see that the image generated from the decoder is changed, right? So the head pose of this image is getting changed because we have changed the latent variable relevant to this head pose of the image. So you can find, if you can find the latent variable that was generated relevant to the head pose, you can change that variable and get the image easily from the decoder. So that is one of the main advantages of variational autoencoders. So in the latent space, there are not only one hidden variables, but there can be many other latent variables, like the variables relevant to smiling nature of a person, right? So in this, so we can have a matrix with the head pose and the smile. So when you increase the head pose, you can change the angle of the head, the pose of the head. And when you change the variable relevant to smile, you can see the increase of the smile with in this direction, right? And head pose in this direction. So you can get a matrix out of these two, right? But you may find that sometimes sometimes there can be situations where, for example, in this layer, you can find when the head is posed, head pose is changed, your smile is also getting changed, right? So in here, the smile is very high, but your head pose is changed, the smile is reduced, right? So that means these latent variables are not that independent, right? Because because the head pose is not independent from the smile. When you change the head pose, you can see the smile is also getting changed, right? So if you want to get these latent variables very independent, right? So reduce the correlation between these latent variables, you want to increase the regularization component of this loss function, right? So earlier we said that the loss function consists of the reconstruction loss and the regularization loss, right? If you want to reduce the correlation in between the latent variables, or you want to make the latent variables independent, you want to increase the proportion of this regularization term in this loss function, right? So you can put some variable, a constant beta to, so which is a scalar value, to increase the weight of this regularization term, so that the loss function is getting more affected with this regularization term. So this beta is when you add the beta like this, so this new type of autoencoder, variational autoencoder, is known as beta variational autoencoder, right? Or Beta-VAE, right? So when you have a beta like in a lower value, when you rotate the smile may get affected, right? So when you, in this direction, when you change the pose of the head, your smile is getting reduced, right? But when you increase the beta to a higher value like 250, you can see even your face pose is changed, the smile is not getting changed because the correlation between the head rotation and the smile has reduced when the beta value got increased, right? So, and also the in the downside that you can say when you increase the regularization, then the reconstruction loss the weight for the reconstruction loss get reduced, right? So basically then the image quality can get affected, right? So in this image you can see that the image quality is high relevant more than this image where the image quality is low, which is kind of blurred, but so that but the variables got independent from each other when you increase the beta. So by tuning the beta value, you can get either the independence for these variables, for these latent variables, or to increase the quality of the images generated from the by increasing the reconstruction loss to the loss function, right? So this is a also a value that you can change in a beta variational autoencoder. So, however, the variational autoencoders or beta variational autoencoders are not that good at sampling data in a very high quality, right? So the idea of using the variation autoencoders is most about generating the probability distribution. So we are trying to model the data distribution in the sample data set in the encoder and the decoder, and we are trying to generate information to generate samples from this distribution. But if we want some diverse kind of data, and if you are not that much concerned about the distribution itself, then you can use the generative adversarial network. So with generative adversarial networks, you can generate very high quality images, right? So we will see why they are very high in quality, right? So it is based on the nature itself. But however, the downside is that training a generative adversarial network is a bit expensive when it comes to the computation power required and takes a lot of time. But it is very effective when you have a little amount of data and you want to have very high quality sample data generated, like the high quality images generated, for example, where you want to create some images which are very independent or very novel or very creative, which are not taking the exact features from your dataset. So then these generative adversarial networks can be used. So let's see how the GANs are working. Right? So GANs are generative adversarial networks are small, in simple called as GANs. There are two neural networks that are training together in this generative adversarial network. So one neural network is known as the generator, which is based on the generative models as we have discussed, right? And there's a discriminator, right? Which is also a neural network based on a classification that we know, right? So maybe some feed-forward network followed by a softnet classifier or something like that, right? So if it's a binary classifier, you can use a what do you mean this logistic regression or whatever, right? So this is a discriminator and this is a generator. So these two neural networks are training together, but with opposite objectives. Like they are fighting with each other. When one is getting higher quality, when one is getting higher accuracy or lower loss, the other will have higher loss. So it is trying to increase the uh, it is going to change more, and then the other will get affected, right? So that is the nature of this generative adversarial networks, right? So that is exactly the same reason why these generative adversarial networks can generate very high quality data, like very realistic images, right? So once you have once you have trained the generative adversarial network, uh, the generator which is generating, for example, if say, for example, it's a image related generative adversarial network. So what the generator does is it to generate new images, and the discriminator is trying to find whether this image is a generated image or not a generated image. So generator generator and the discriminator are competing with each other. Generator is trying to generate images that are not uh, distinguishable from the real images. That means generator is trying to fake the discriminator and trying to generate very realistic images. The discriminator is trying to the discriminator's objective is to identify whether the generated image or the real image is a real one, right? So he's given discriminator is given both the real images from the dataset and the generated uh, images, and the discriminator has to find whether these images are real or which one is the real one, right? So when they are competing with each other, the generator will get very successful, very competitive at generating images, and that generator can be later uh, uh, taken out from this GAN, and we can use it as a generator to generate new images, right? That is the idea of using this GAN. So let's draw it in this block diagram. So this is the block diagram for this, for a GAN, right? So like the autoencoder, the same kind of notation are used, right? So in here, instead of using a latent space, we are starting with noise, right? So in autoencoders so same, right? So we start with the noise, and there's a generator network which should be having internally some layers of neural networks which are increasing in its size, and it is generating a high dimensional x values which can be represented as x fake, and there are another set of x data, or it may be uh, relevant to the real data. In this example, we can say the image data set that we are going to use for this GAN are given as x real. X fake is completely generated by this generator network, which is represented by G. This is the D, which is known as the discriminator, which is trying to identify whether this one is true or this one is true, right? So it may either find this one is false and this one is true. So then the discriminator has failed, but generator has got successful because generator could fool the discriminator, but discriminator has failed because it couldn't distinguish between the real and the fake. So discriminator will improve while the generator will not. When the discriminator getting successful, when the discriminator can identify this as a fake and this as a real, the discriminator will get a higher payoff, or it will get successful, but the generator will fail. So it would be given a negative feedback, and it would be trained in the other direction, right? So this generator and the discriminator will be training against each other, so that both will be get better with time, right? Your data set is given as this X real. So what happens later is one of them would dominate, right? So we will say what happens. So the intuition of this scan can be explained like this. So say, let me draw it in this way. Say these are the generated data points, and these are the real data points. At first, because these are generated, and these real fake data points are away from these real data points, the discriminator can give higher probabilities for each of these. These are the probabilities in the probability levels, right? These are the probabilities, and these will get lower probabilities because they are outside this domain. But later, these this generator will identify that he got unsuccessful because their data points were located outside this real data point. So it will try to move the generated data points near the real data points, right? So then what happens is, with the time, the discriminator would not be able to distinguish between the real data points and the fake data points because they are so close together in the one-dimensional space in this case. So it would fail to discriminate very well. So finally, when in a successful training session, the discriminator will fail and the generator would be successful at generating highly realistic images. So that is how the realistic image that is how a realistic image generator is created, right? That is how the generators can in the GAN can generate highly realistic images. So you might have seen in that in the trend of generative adversarial networks, you might have seen some real like faces, but who have people that may not have existed in the world, but are generated from the neural network. So most of them were generated from these generative adversarial networks that we have learned today, right? So when it comes to the discriminator loss function, it is calculated like this, where you can get the x value and whether the x value got fake, which is the z value is operated on g, and it is calculated whether it is fake, and whether this x got fake, which is where the real value got fake. One minus real value, one minus fake means it is real. So this is the real. It is being real value being real, and this is the generated value being fake. So this is how when those two are good, so then the discriminator would get better, right? So that the discriminator wants to maximize the discriminator. It wants to maximize this loss function. But for the same value, The generator wants to reduce or minimize this discriminators values generated GZ, generated discriminated and identified as fake values and real values not identified as fake values should be reduced or minimized for the generator. So they are because they are competing with each other. So the loss function for both of the generator and the discriminator can be described as this. Right? So this is the loss function for the generative adversarial network. And this is what happens once you have trained a generative adversarial network and how to use it. Right. So once you have learned with the once you have learned your generator, so what you are interested at last is training the generator, right? So because generator can generate images or whatever the data that you want to generate, right? So this is what happens at the end of the training session. So this train generator would map to a Gaussian distribution in the Z space, because when you are training a latent space, naturally it would follow a Gaussian distribution, right? So in a certain point, if you take a random point of this Gaussian space, this generator would create a certain image in the real image space, right? So this would be a complex space in the multidimensional space vector field relevant to the images, the real images. So it would be relevant to this. This black zone would be relevant to this particular data point. So if you take another random data point from this Gaussian distribution in the Z space, generator would generate another real bird image data point from the real image complex data space, which is this one, right? So if you take this point relevant to the black zone and this point relevant to this particular bird, you can have two different points, right? So if you try to change the vector from here to here, little by little, the generator would move the image generated from here to here little by little. So it starts, so in this point, the starting image would be a black zone like this. At this point, at the end point, the image would be an bird like this, would be a bird like this. And when we are moving from here to here, the bird that is generated would be changed little by little until the final bird is created, right? So now you can see how the birds generated are changed when you have intermediate values for this Z vector, right? So these are some intermediate values in between these 2 points. So that this is how the bird image got evolved when you are changing this Z value from here to here. So this is a very interesting thing, right? So you can generate, once you find two different data points in the Gaussian space or the Z space, then now you can get something in between so that you can generate the image in between these 2 points, right? So this is a very interesting thing that you can do with a generative adversarial network once you have generated the generator correctly, right? So there are certain types of generative adversarial networks. So one is known as the progressive growing GAN, right? So in the progressive growing GAN, what you can do is you can you can give a low resolution image with generator with 4x4 layers, and by progressively growing the size of each of the layers, you can improve the resolution of the image, right? With the training process, you can increase the number of layers, and in this layer, you can get a 1024 by 1024 resolution. Then you will get a very high quality, high resolution image. Then you can generate from the very low resolution image. So this is another good application of GANs, which is known as the progressive growing GANs. So there's another type of GANs known as conditional GANs or C-GANs, where you can add the conditional factor, which is either a label to both. We can give them to the both discriminator and the generator like this. Where if you want to segment the street view into several sections, then you can give it into the generator like this, and you can give both generated one and the original one as a couple of as a pair of image to the discriminator, and the discriminator can find is trying to discriminate whether this pair is real or not. So with this one, you can create a generator which can generate real street views from a classified image, or create a classified segmented image out of the original street view, and so on, right? Or you can get in the Google Maps, you might have seen that you can have both street views and the satellite view. So you can use this kind of conditional GANs to generate the street views from the satellite view. In the other way, a satellite view from the street view as well, right? So in those cases, you can use conditional GANs. So you might have seen this video in the Facebooks maybe sometime back. So these are two videos where when you can get the recording of this horse running. So it is this horse running video is converted into a zebra running. So which is an application of this particular type of GAN, which is known as a cycle GAN, where these two networks are sharing the feedback with each other. So one network can share the some of the styles of its network with the other network, and it can generate a new type of information influenced by the original type. So this is known as the cycle GAN. So this is another application of generative adversarial networks, right? However, these variational autoencoders and GANs have some limitations. Like when you are generating images, that means when you are training it more and more, the images or the data that are generated by this variational autoencoders and GANs are having an effect known as regression to the average. So what it means is that when you are training it more, the images generated by these generator networks in the variational autoencoders and GANs are generating only some of the only images that are similar to some of the very common images of the dataset, right? So in other words, the generated images will be very similar, so that it would be very boring and less diverse, right? So less diversity is also another problem, where you can't generate a data that is much more diverse than the original data set, in some cases with variation autoencoders and GANs, right? So you can generate some diversity, but not that much diverse data by extracting the information. So that is another drawback in the VAEs and GANs, right? And when it comes to training, so they are very computationally expensive, and when it comes to stabilizing, so that is very problematic, especially when it comes to the GANs, right? So when you are, because both the generator and the discriminator are training against each other, sometimes they may not, this system may get unstable, right? So some one would get better and it is trying to be better and better, and the other one is lagging, or some they are not getting, no one is getting better, or something like that can happen, where the system will get, the total system will get unstable when you are changing some of the things even a little bit, right? So that means you can't uh, robustly change the data sets and use the same training process with GANs. So that is a common problem with relevant to the relevant to training generative adversarial networks, and it also takes a lot of time than conventional supervised learning algorithms, right? So one of the latest innovation relevant to this generative model is known as diffusion models, right? In diffusion models, we use another somewhat different concept known as the diffusion. Diffusion means added entropy or the noise into the images, which is influenced by the theory of thermodynamics or physics, right? So the information or the noise information is getting lost and the noise is added into images, which is known as the noising, right? So here what it happens is we would have a noise function where you can add some noise into a given image, right? So that has no relevance to the machine learning, but you generate some noise, then you add it into a image, and then you would get a noised image. So you can use the same noising function to this noised image and generate an image with even more noise. So this image can be applied to this noising function and add more noise and more noise until all the data are gone from this original image, right? So this is known as forward noising. So you can apply this noising function, which is not relevant to the machine learning or deep learning. So this you can use, this is just a function that can add noise into the images. You can apply it in this step. You can move to this step, and once you apply this function to this step, you will go to this step, and this step, until all the information in the original image got lost. Now, what we are trying to do is we are trying to go back to this original image in all the steps that we have come across in backwards until we go to the first original clear image using a neural network. So in the world of variational autoencoders and generative adversarial networks, what you do is a one-shot learning, where you get some noise and then you generate the image out of this noise, right? From Z to X. But this process is not that stable, right? So you can't scale it that much as you wish. So that is the problem we had. So in diffusion models, we don't do it in a single step. So what we do is we apply these autoencoders like neural networks in several steps actually the same network is applied in several steps to uh, this noisy image to make the noise lesser and lesser until it comes to the original generated sample, right? So this is in diffusion, it is an iterative process where you use a neural network again and again instead of trying to make the original image in a single step. So that this is the main difference between the variational autoencoders or the GANs with the diffusion models. So if you take this noising process as and we name it as t equals 0, 1, 2, 3, and 4, right? So this is the image that has no information but 100% noise. So now what we are going to try to do is we are trying to learn a denoising function with the neural network when you are given the image in the time t, how to get the earlier time step or t minus 1 using a neural network. So if you are given the image relevant to t equals 3, right? Then you are trying to learn a neural network to convert it into the image in t equals 2, which is this one, right? So from T4 to T3, T3 to T2, T2 to T1, T1 to T0. In all the cases, you can use this diffusion model, the same neural network to reduce the noise and add information into the image, right? So we do it step by step, not like in the AVNs and AVEs and GANs, but by step, we try to denoise the image. So for all the data points, so if it's a data set of images, we have a lot of images, right? So for all the images, we create, if we take t as 4, uh, t as the number of noising steps as 5, right? So we have 5. We generate 5 noise generated images, and we are trying to train our neural network to give the image relevant to the time t, and predict the t minus 1 image out of this data set, right? So in this case, the diffusion models are working highly successful with relevant to the variational autoencoders and generative adversarial networks. In these diffusion models, the time step t is encoded in an embedding similar to the positional encoding in transformer models, where you can use sine waves to identify what is the position or the time step relevant to the this particular image, so that the neural network can get some idea what is the noise level that would be there in this neural network, so it can reduce the noise. So that is how a diffusion model works. So yeah, so this is all for the today's lesson. If you have any questions, you can ask.